Hello and welcome back. So this week we'll continue with where we left off last time. So where we looked at convolutional neural networks and the various operations in it, primarily the convolutional operation using filter kernels as well as the max pooling operation. Okay. So this week we'll look at CNN training to some extent, also to look at semantic segmentation. So as far as CNN training is concerned, the algorithm for training is the same, in the sense learning is the same, the gradient descent, and the backpropagation algorithm is used to estimate the gradients of the weights in the different layers, in the filter kernels in the different layers. However, we are going to look at certain techniques which are adopted primarily for CNNs in many cases. One is called dropout. This is used for regularization. Some normalization layers, basically batch norm is one such technique. We'll look at what that means. And finally, a small note on hyperparameter optimization to wrap up some aspects of CNN training algorithms. So we'll look at dropouts first. So dropout is a regularization technique. Okay. So regularization technique. So the idea is the following. So we want to reduce the gap between your training and test error. So typically after you finish training a fairly large neural network, especially CNN, let's say for medical image analysis, the training error might be very small. So for instance, if you're, let's say, doing classification, for instance. So let's assume that you're trying to classify chest x-rays into two classes, abnormal versus normal being any kind of abnormality, and you have, let's say, 90% accuracy. We want to look at sensitivity, specificity, etc. But in general, you say they're all pretty good and we have 90% accuracy, let's say. And this is your training accuracy, okay? Training accuracy. And if you take a test data, new data comes in, it is test data, maybe the performance is not so good. Most of the time, it's not so good. But you would not want it too far away. Let's say you don't want your network to perform 60% accuracy on test data, right? So you would rather have it perform at 95% or even 90% on test data. That's what you want. So which means that we are trying to narrow the gap between the training performance and the test performance. Okay. And that for that purpose, these dropouts are used, and they act as regularizers. Because if you think of regularization, what it does is to make sure that your parameters don't memorize. Okay, so don't memorize the data. So what happens is, because CNNs have a lot of parameters, especially in the last few layers, when especially for classification, when a lot of the layers are fully connected, there's a tendency to overfit. Overfitting is when your network memorizes the data, so it will fit the trained data very well, but when the test data comes in, you have a very poor performance. Okay, so to reduce that gap in performance, you do this regularization, and dropout is one form of regularization. So what exactly happens in a dropout? So in a standard dropout regularization, okay, what we do is we zero out some fractions of the hidden units, okay, in every layer, and then we kind of compensate for it, or debias the layer by normalizing some fraction of the hidden units, okay, that were not dropped out, that were retained. Okay, so which means that we can write it in this form: your hidden unit that you retain, h prime, is 0 with probability p, right? And it switch over 1 minus p otherwise. Okay, so if you calculate the expectation of h prime, it will turn out to be h. Okay, so in expectation, that's you get the hidden units that you would like. So we illustrated this in the picture here, where you have on the left hand side in this picture, the network is bottom to top. The input layer is the x, the hidden units are h, and the output layer is o. And so in this layer, in this particular example, before dropouts, all the neurons are connected to all the other neurons, in the sense between layers. But when you apply dropout, what you do is you zero out some of the neurons. Here neurons H2 and H3 has been zeroed out here. That's why you don't see them there. And then you train the network as it is. So in every epoch, you would drop out some of the neurons with a certain probability. Okay, and then you compensate for that or debias that by scaling the existing the retained neurons or the hidden units with 1 minus p. Okay, so how does this help? So in the original paper which talked about dropouts, the explanation offered was that while training, it can happen that certain sets of neurons can get can co-adapt. Okay, which means that they just don't learn independently, but they rather depend on what their input is. So if there are multiple hidden layers, let's say I had one more hidden layer somewhere there, the argument is that the neurons in this or the hidden units in this layer will not learn the features independently, but rather it will learn based on what its inputs are, which is basically coming from H1. So these two layers might co-adapt. Okay. So to make them independent, what you do is you cut out some of them. Let's say in this case we have cut out H2 and H5. I'm sorry, I just said H1, H2 here previously. You cut out H2 and H5. So that way, the next layer will learn to impute, in the sense it learns to learn without the presence of these two hidden units. Okay, so you train the neural network this way. You don't overfit. You have this regularization effect, and your training and test accuracy specifically improves. Okay, so the way to implement this is for every hidden unit in every layer, you would sample from the uniform distribution, retain all the neurons or hidden units with the associated probability greater than p, while throwing away all the neurons or the hidden units which have associated probability less than p. Now remember that this is done only during training of the network. So whenever during training, every epoch, you would go through every layer and you would drop certain hidden units or neurons, as I call them, with a certain probability, and you keep doing that till the training completes. So now once the training is done, you would just keep the network as it is and then do your testing. Okay. However, some people have used it, some researchers have used it to classify, misspoke, to estimate the uncertainty in the prediction. So one way to do that would be to drop out, have multiple forward passes for prediction, and each forward pass you would drop out certain hidden units just to see the variability in your output. Okay, so another way of looking at it is that since the neural networks, you can think of them as a function, all you're trying to do is to figure out a smooth function, right? So that small changes in your input does not radically affect the output. So that's another way of looking at this regularization effect offered by the dropouts algorithm. So you can use this typically in the fully connected layers of a network, which happens in a lot of classification networks. If you looked at the ones that we had reviewed last week, the last couple of layers are fully connected, and that's where a lot of the weights occur. So a lot of the dropouts is actually performed only in those layers, mostly in a lot of the implementations. Of course, nothing is stopping you from doing it in the earlier layers, in the convolutional layers also. Yeah, so when you do the dropouts in the fully connected layers, you can do several forward passes given a test data just to quantify, the uncertainty in the predictions. Okay, that's one trick that people have also used. Okay, so that's dropouts. So when I say regularization, that's dropouts is one technique. The other techniques for regularization, which is more standard, referred to as weight decay. So here, this is how you would do it. Let L of y comma y hat be the loss function. Now y hat is the output from the network. Okay. Let's say estimate made by your network, y is your ground truth. Now you would add to the loss function, several terms weighted appropriately. So there is this hyperparameter alpha, which would weight, we'd call this and we'll also have this beta. I'll just do it this way. W is 1 here. So this one, it's the this is the L2 norm supposedly. So if you had n weights in your neural network, n is the total number of weights in your network. Your standard weight decay, that's what it's called in the neural network parlance, would be just W1 square plus W2 square, so on and so forth, W1 square, okay? And of course, you have to multiply this with the hyperparameter alpha. You have to choose alpha by hand. You have to do that validation study. The other version is you add the absolute values W1 plus W2 plus all the way to Wn, okay? N is the total number of weights, okay? So I'm using this as N. N is total number of weights, you will return that, okay? So these are the two standard regularizations, okay? So what this prevents, if you look at the standard weight decay where you add the squares of the weights, this will prevent the weights from taking very large values, okay? So some outsized value for any of the W's will be severely penalized, okay? So on an average, all of these weights will be very small. So in the sense that they'll be driven to smaller and smaller values that is closer to 0. That's why it's called weight decay. All your values of W, because if the value of the weights fall less than 1, let's say all the weights are your magnitude is less than 1, then Wn square becomes even smaller, right? Or W2 square or W square becomes even smaller, right? So in that sense, you're driving your weights to smaller values. That's why it's called weight decay, and it distributes the weights across a very large number of features, making the network more robust. Okay. On the other hand, the L1 based, which is basically the absolute values of the weights. So this is one other regularization technique. Here, this leads to a lot of the weights going to 0, while retaining very few of the weights with a very high weightage. And so this is sometimes not preferred when you want to estimate when you think that your model relies only on very few features. Okay. Again, this is not necessarily only for neural networks, but any other machine learning model. Okay, so in this video, we will look at batch normalization, which is like a very popular technique. Should I say it's there now in all deep neural networks, and is possibly very effective because it helps to accelerate the convergence of deep neural networks during training. Okay, so the paper that came up with this technique wrote it to address the so-called covariate shift, but later works have shown that maybe that is not the correct explanation. Okay, so we'll just talk about it briefly, and then we'll also see what exactly the computations are for batch normalization, and of course there is a related normalization technique called layer norm. Okay, so we'll look at that also. Okay, so when we think of this neural networks, okay, let's look at the inputs to a neural network, right? So we can first consider even fully connected feed-forward neural networks, multi-layer perceptrons, for instance, where inputs are a bunch of features. So typically what we would do would be to make sure that we pre-process the data, and that has a huge impact on the results, right? So we would typically pre-process the data to have zero mean and unit variance across multiple observations. So we will take our entire training data and subtract the mean from it and divide by the standard deviation to make it zero mean and unit variance. Okay, so this is one of the pre-processing steps that are usually done. Okay, the idea behind doing that is that if you consider your loss function as a function of the weights, okay, so you have these features, and you can't have these features these pre-processing techniques help with the optimization, right? Because it puts all the parameters on the same scale. Okay, So very simple example, usually if you want to think about it, let's say you have two inputs to my neural network. Okay, I have two inputs, call them x1 and x2, and let's say there's a bunch of weights connecting them. We can just say I have from a very in fact from a very linear regression point of view, w1 w2 are the weights multiplying them, and I have an output. They provide a y hat, okay, as an output, which is basically y hat is w1 x1 plus, let me rewrite this, it's gone out of scale. So I'll rewrite output y hat as w1 x1 plus w2 x2. Okay. Now, why do we want the inputs x1 and x2 to have zero mean and unit standard deviation? That is the standardization, so that they all have a similar scale. That's what we want to do. Is that it helps in better optimization, because if let's say x1 occupies a range of 0 to 10, okay, and x2 occupies a range of 10 raised to 5 to 10 raised to 7, okay, which would mean that we would have to adjust w1 and w2 differently, right? Because w1 should have to, either w1 has to be so high in order to bring this sum of products to comparable to w2 x2, and in that case w2 x2 has to be very low, okay. So which means that when we take steps in the gradient descent direction, the step size would have to be very different for w1 and w2, okay, which makes the optimization much slower. So in order to prevent that, you would typically scale x1 and x2. Various ways of scaling it. One is to make sure they have zero mean and unit standard deviation. Of course, this is across the training data set. So there are many training examples. You have, let's say, M training examples. So then you would average across the M training examples and then find the standard deviation across the M training examples and do the appropriate normalization. So this helps the optimizer in the optimization process. So, but if you think of a neural network, so this is just for I've done this for a very simple linear regression kind of model. Okay. Now, if you consider a deep neural network, there are multiple layers, right? And during the initial stages of the training, as the data comes at the input layer, and then you have the multiplication with the weight matrix, non-linearity, forms the first hidden layer, and so on and so forth. So initially, when the weights are not trained, then even though in the input layer you make them let's say zero mean and unit standard deviation, as it goes into the various layers, that standardization is lost. Okay, and it would be nice if we can arrest this drift, in the distribution, if you can call it, because as we go, the input has been now. We would start off with the values zero mean and unit standard deviation have now gotten strange, okay, because of multiplication as well as application of non-linearities through the layers. Okay, so the paper suggested this technique to maybe put it back into the same standardization that we send the inputs. Okay, so the way to do that is the following is given in this flow chart right here, where you have the x is your input. X is a vector, okay, and m in a mini batch there are m examples of that vector, and we actually learn the parameters in order to standardize them. So how do we learn them? The way to do that is to calculate the mini batch mean. That's what it does, mean of the x, the input vectors. Of course, when I say mini batch mean, this is the input to the particular layer. Right, so that's the thing. The x is the input to any of the layers that you are considering. It need not necessarily be the input layer, but some layer in between also. Right, so you calculate the mean of the inputs, you calculate the standard deviation of the inputs, and then you do your usual standardization, the x minus mean divided by the standard deviation. But what you do is you rescale them using a learned gamma and beta. Okay. So the scale and shift parameters, gamma and beta, you learn, and because these are free parameters that are learned by the network. Okay, so for every you would learn this as a layer. So for every neuron and layer, you will learn some parameter like this. That's one implementation, correct? So just to reiterate, the idea is you would calculate the mean and the standard deviation of the input to every layer over the mini batch, okay, for every neuron or every hidden unit, and you would scale your inputs like we did for the actual input of the neural network. In this case, you're normalizing it so that it's zero mean and unit standard deviation, and you will scale it by using a learned gamma and beta, okay. So this process, this is actually like a layer that you can drop in wherever you want inside a deep neural network and train, because you'll be learning gamma and beta as parameters also. So batch normalization has shown to be very useful in accelerating the training. So very deep networks train much faster, because that has been proven. Now, the way batch norm is applied during training is different for different type of networks. So, for instance, for fully connected layers, okay, you would, in the original paper of the batch normalization is applied after the linear combination of the activations from the previous layer, and following which you apply the nonlinear activation. Okay, of course, people have experimented with it by applying the batch normalization after the activation function. Okay, so that's also there. So there is also, of course, some debate about which is more effective. Okay, so you can do either way. Okay. The other thing to consider is that, when you do the batch norm in a fully connected network, recall that we do this mean of the inputs to each layer across the mini batch. So every hidden unit or neuron in a layer is treated separately. You don't average across the hidden units in a layer. Now, when you apply this the convolutional neural network, okay, once again, we can either apply it after the convolution and before the nonlinear activation. Okay. This operation is done on a per channel basis across all locations. Okay. So, which means that the key, similar, if you want to do something similar in a fully connected network, it would mean that we are averaging across the hidden units in a layer. Okay, which we don't do actually. But for convolutional neural networks, when you do this normalization, it is normalization per channel. When you do it for a fully connected feed forward, ML neural network, the normalization is per hidden unit, okay, or per neuron. Okay. So just to reiterate, for the convolutional neural networks, we would carry out the batch normalization per channel, and we would consider the mini batch per channel. Okay, so we consider mini batch per channel to calculate the mean and standard deviation, and then normalize the inputs to every layer. Okay, and each channel will have its own scale and shift parameters. Okay, and they are scalars, right? So, but for a fully connected, we saw that every hidden unit will have its own scale and shift parameters that are estimated during backpropagation. Okay. Now that we know this, we can now look at layer norm. Layer norm is very similar, and except that we just do it for one observation at a time. Especially for CNN, it's very well defined, because every channel has a feature map, and we can average it spatially. Okay, so the formulas remain the same, except that the mu that you estimate here, is over the dimensionality of your data. So I'll quickly write this down here. Your mu layer norm, I'll call this layer norm, is 1 over, in this case, I will use n, where n is the number of number of dimensions. So every x is a n-dimensional vector. So you will just average over your vector dimensions. Similarly, you have a corresponding formula for the standard deviation, the variance. Okay. So the layer normalization doesn't depend on mini batch size. Okay. and we can do it for both train and test. Okay, and it actually just some deterministic transformation. Okay, so and basically it also helps in optimization. There are more details given in the publication. Just search for layer norm, and you will be able to find it. During prediction, that is when you are testing with new data, then we might not have the luxury of running through every mini batch statistics that we calculated in order to make a prediction. But rather, the statistics is estimated, that is, the statistics for the mu b and sigma b that we see here. That's the one that we need before we make the predictions. It's usually gathered over the entire data set when the predictions are made. Okay, so we're now going to look at this hyperparameter optimization, which is again a very key concept to understand when you are trying to train deep neural networks, or for that matter, any kind of machine learning based algorithm. Okay, so as we saw in the previous few videos, there are several hyperparameters involved in training CNNs. Okay, so for instance, we looked at dropouts. So when you say dropouts, for instance, say dropouts, there is this parameter p that you have to figure out. Okay, what is 0.25, 0.5, 0.1, etc. Right? We also looked at batch normalization. Okay, so batch norm, once again we have to decide how many such batch normalizers do you need. Do you need that in every layer? Do you need that only in the earlier part of the network or in the later part of the network, so on and so forth. Okay, so that's a decision you have to make. We looked at this L1, L2 regularizers, which are pre-multiplied by this alpha and beta. These are again scalars that you have to estimate. What is the correct value for these scalars? Do we need both L1 and L2? That's one other problem. That's one other hyperparameter. So these are all hyperparameters. In addition to whether number of layers in a neural network. Okay, how many filters per layer, right? And we didn't go through gradient descent algorithm in detail, but gradient descent algorithm has a parameter called the learning rate, which is again a hyperparameter. Okay, so how do we figure out the correct values of these things? Because these are not learned during the training of a neural network. Okay, so learned, these something you have to fix. Okay, so the way to look at it is to put them in a grid. Okay, so there's only a range of values that they can take. You would put them in a grid, multidimensional grid, and perform the grid search. That would be the best way to do. So grid search is where you systematically step through the values of each of these parameters, and you would estimate a curve. What is this curve? This is shown by this green mount here. This curve is some metric that you would, for instance, the loss function itself. For a certain value of these alpha, beta, and p, what is the best loss function you get? Okay, or what is the series of loss functions you get for each combination of this alpha, beta, and you would take the combination that would give you the least in this case the least loss function. Correct. So loss function is one metric. You can do other metrics also. Okay. So a grid search is where you would systematically step through each one of these parameters. Okay. So, but the problem with this grid layout is actually shown in this picture is that maybe your optimum is right here, but when you do a systematic grid search, you might actually miss out on it. Okay, and so you won't be able to sample this error surface as properly, right? So because why would you call the error surface? Because if you think of these hyperparameters, let's say even take three of them, the dropout with a probability p, alpha and beta. Let's say these are the three parameters that you are trying to optimize, hyperparameters that you want to estimate. Then you can, on a small portion of your training data, estimate the loss function as a function of these three parameters. And that's what I call the error surface, right? So if you don't sample these properly, which happens when you do this systematic grid search by sampling these parameters at regular intervals and running your training at all combinations of such parameters, then it's a good chance that you might miss out on the optimum. Okay. On the other hand, if you do a random search of your grid, like you do have these parameters, ranges of these parameters, but then you pick them randomly, there's a good possibility that you would be able to come near the optimum value. So typically you do it in a kind of a nested fashion where you would do a very up course search, random search, and basically random sampling, and then maybe when you are near an optimum value, you would then grid and then do a much more systematic search. Okay, so all of these are possible. Of course, the least recommended is the hand tuning, wherein you just randomly try a few parameters and you're happy with the results, and mostly those turn out to be either overfitting or underfitting. Okay, so that's a bad practice. So random search systematically on all the hyperparameters would give the much better results.